Hi, this is Dr. Remenacker. In this particular video, we're going to start on a topic that I always look forward to getting to. It's the idea of optimization. Optimization can either talk about making something as large as possible or as small as possible. For example, in a business setting, you want to optimize some things like customer service and profit, and there are some things that you want to minimize like waste. Okay, so realize that when we're talking about optimization, it can mean maximizing or minimizing, and it's purely dependent on the context of the problem as to whether we're looking at maximizing or minimizing. Okay, we're going to look at optimization. Regardless where you're headed, business or industry wise, decision making, this is going to come into play. Okay. One of the things that's critical is being able to make decisions founded on quality decision-making processes. These techniques that we're going to look at are the basis of those quality decision-making processes. Okay, we are going to look at the situations in terms of one variable. By being in one variable, for example, x, it will allow us to be able to create graphs. Okay. We'll have our value for x, and then, of course, we'll have a value for y. In the real world, it is very rare that you only have one variable. For example, if you take a grocery store, every product in that grocery store can be represented by a different variable because the profit margin on each item is different from the others. If you go into a large, well-stocked grocery store, you can have tens of thousands of items, which means you now have tens of thousands of variables. In that case, there's absolutely no way we can get a graph in two dimensions to represent our costs, our profits, our revenue, or anything. So what we're going to develop over the next few videos is a technique for locating maximums and minimums, okay, based on strictly calculus. Now I realize that at this point, you can have graphs like g of x here. And it's very easy to just look at the graph and say, well, here's a maximum, here's a minimum, here's a maximum, and do stuff like that. However, in the real world, most of the time it is impossible to get a graph. In the case of the well-stocked grocery store, you would need a graph that can handle 10 or 15,000 different dimensions. It just doesn't happen. Using the calculus that we've looked at thus far, derivatives, we can determine if a function is increasing or decreasing. It's important to know if, for example, costs are going up or going down, if your profit is going up or going down. The way that you determine increasing or decreasing is by looking at the slope of the function at a particular location. So for example, on this graph here, if I were to choose, I'm going to label this as point B right there. And I wanted to consider the slope. Now remember, we've talked about this a number of times in earlier videos. Derivatives are slopes. Okay, so if we were to take the derivative of our function and evaluate it at this location, B, in this case, the slope is positive. So the derivative would be greater than 0, which would mean that the function is increasing. It's going up. Okay. So if we were talking about profit, that would mean as we move from B to a number slightly bigger than B, the profit would go up. If we were talking about cost, as we go from B to a value slightly bigger than B, the profit or the cost would be going up. Not often the case that you want to increase your cost unless you're really going to increase your productivity and your profit. Let's take a look at a second point here. I'm going to move a little bit to the left. Let's say we're at point A. At this point A, if we were to evaluate the derivative and substitute in the value of x at this point A, notice here it's in a location where the slope is going down. In other words, it's a negative slope, which means that things are decreasing. If our function represented profit, this would be a problem. We don't want profit going down. If, however, it represented cost, that's not a bad thing. Costs are going down. Okay. Let's take a look at an example of a function, just one variable for right now. Actually, we'll get into multiple variables as we move into the second semester of calculus, but for right now, we're going to stick with just one variable. Let's say we have something like k of x is going to be 1/3 x cubed minus x plus 2/3. And what you need to determine here is, where is this function increasing? Where is this function decreasing? Well, as we just saw in the graph and the conversation we had there, when we're looking for increasing and decreasing, what we're really looking for is situations where the slope is positive or negative. The slope positive or the slope negative means the derivative greater than 0 or the derivative less than 0. Well, what this means is we first need to compute the derivative. And the derivative here is going to be the 3 times the 1/3 is just going to give me x squared minus 1. Okay, so we have this. Now what we want to do is we next want to determine where is the derivative 0. And you might say, that's kind of weird. Why would I be concerned about the derivative 0? Well, the reason that we're concerned about the derivative being 0 is we're going to have something like this. Our graph is going to do something like this. Just kind of roughing it out here. This is not the derivative of the graph. This is the graph itself. There are two very important locations on this graph. One of those occurs right here. It's a maximum. At the maximum, the derivative is 0. Okay, remember the slope of the tangent line there is going to be 0. Similarly, over here a little bit to the right, we are at a minimum. Once again, the derivative is going to be 0. The tangent line has a slope of 0. Realize that our maximums and our minimums will always occur where the slope is 0. Okay, these are going to be high points and low points on a graph, or they have the potential of being high points and low points on a graph. Okay, so to locate changes in increasing and decreasing, we're going to compute our derivative, which we have over here on the left-hand side, and I'm going to set it equal to 0. Do not overlook this idea of the derivative equal to 0. Okay, I want to emphasize we do not set the derivative equal to 0 because it's easy to solve. We do not want to set the derivative equal to 0 because 0 is a nice number. We set the derivative equal to 0 because we want the slope to be 0, and the derivative is a slope. We're looking for, where is the slope 0? So what we're looking for is, where is the derivative 0? That is the reason why we set the derivative equal to 0. That is a real important idea, and it appears often on quizzes and tests. Just a thought. Okay, so as we go about solving this, we're going to have x squared equals 1. Taking the square root, we get that x is equal to plus or minus 1. This gives us two locations where we have a potential maximum or minimum, because these are locations where the slope of the function is 0. Okay, there are several ways to determine what's going on. One of the ways to do this is to create what looks kind of like a number line. I'm going to put my -1 for x here, my +1 for x here. Then what I'm going to do is I'm going to evaluate the derivative on each of the intervals that you can see. So for example, to the far left, I'm going to evaluate the derivative for some x value over here. Now, if you look up at the green graph in the upper right-hand corner, you can see in this area that the function is increasing, which means that the derivative should be positive. Well, to verify that, all I'm going to do is I'm going to take my derivative, pick some number to the left of -1. It could be some strange things like a -75/16. It could be -infinity. I'm going to keep it simpler. I'm going to just pick -2. If we evaluate our derivative, which is in the upper left corner here, if we evaluate it at 2, what that says is we're going to take a -2 squared minus 1, and you can see that's greater than 0. So on this interval, from -infinity to -1, the derivative is greater than 0, which means that the function is increasing. It's going up. It has a positive slope. Moving over to the middle interval, that's the interval between -1 and +1, I'm going to evaluate my derivative at some easy number on this interval. It doesn't matter if you pick an easy number or a hard number. You don't get a better score by picking a really hard number. In fact, you might get a lower score because you make a mistake. Between -1 and 1, a really easy number to pick is 0. If I evaluate my derivative, which is going to be the x squared minus 1, that's going to be 0 squared minus 1, which is a negative value. Okay, because 0 minus 1 is negative. So that tells me that on this interval here, the slope is negative. Now, if the slope is negative, that means it's going down. It is decreasing. Then I'm going to move to the third interval. Well, the third interval is from 1 all the way over to infinity. I'm going to pick some number on this interval to work with. I could pick 6,236,487, but hey, I'm going to try and keep it simple. A number to the right of 1 that's easy to work with is 2. This is going to give me then, evaluating my derivative at 2, 4 minus 1's greater than 0. That means that my derivative here is greater than 0, which means the function is increasing. Notice that for each of these intervals, the conclusion as to what the function is doing truly matches what's happening on the graph. Increasing, decreasing, and increasing. This is really nice because it allows us, without a graph, to determine where is the function increasing and decreasing. This idea of determining where it's increasing and decreasing is very important. If a function goes from increasing to decreasing, like right here on this interval, it means that the function is changing from going up to going down. Where it changes directions right here is what is called a critical value. This is called a critical value because the graph, the function is changing directions. It's changing from moving upward to moving downward. Now, as you can see drawn here by the blue lines, if you change from moving up to moving down, this is a max, a maximum point. Okay, That's why it's critical. If we look at the second interval, okay, if we go from here to here, the function is now going from decreasing to increasing. Once again, we have a change in direction. This is referred to as a critical value. And in this case, if we're going from decreasing to increasing, as drawn right there in the green lines, this is a minimum. Critical values are locations where you change directions from increasing to decreasing or decreasing to increasing. We'll see other situations as things progress, but critical values occur where the derivative is 0. There's a second location where these can happen, and that's where the derivative is undefined. We'll take a look at those as we move on. But for right now, we're going to focus primarily on what's going on when the derivative is 0. Okay? Remember, critical values occur at either where the derivative is 0 or where it is undefined. Another way to phrase that is does not exist. Those are critical values. While we're looking at these critical values, we need to realize that each of these, this maximum and this minimum, represents something that has a special name. It is called a relative extreme. By relative extreme, relative means compared to things around it. So in this first case where we had this maximum, this point compared to everything around it is higher than everything around it. Okay. Similarly, if we look at the minimum, the location where the derivative is 0 is a relative extreme. It's lower than everything around it. Let's take a look at a couple of further examples. Let's consider something like the following. Let's say we have something like f of x is equal to, let's say 4x cubed minus 9x squared minus 30x plus 25. Okay, so we have this polynomial. Real fair question would be locate where this has maximum and minimum values. In other words, where are the relative extremes for this particular function? Well, clearly in this case, we could graph it because we just have one variable. And this whole semester, we're just going to stick with one, maybe two variables. And that's it. All things that we could graph just to develop the techniques that are needed to move beyond two variables and eventually get up to, dare I say, 10,000 variables. Okay. So for right now, what we're going to do is we are going to use this idea that we just developed. The idea that we just developed being we want to locate where is the derivative equal to 0. Well, to locate where the derivative is 0, the first thing we need to do is we need to compute the derivative, which I'm hoping for this is pretty straightforward for you. 12x squared minus 18x minus 30. Now, really important. At this point, we have the derivative. And remember, the derivative is a slope. Points of interest are going to occur where either the derivative is 0 or it doesn't exist. This is a polynomial, so there are no locations where this thing's undefined. So the only consideration for us is going to be, okay, where does this equal 0? Hopefully you have your calculator programmed for the quadratic formula. To find where this is 0, you just put in 12 for A, negative 18 for B, and negative 30 for C, and out come two answers. You get values x equals -1 and x equals 2.5. Okay, so it's really kind of handy to have that quadratic formula programmed into your calculator. It saves a whole lot of work. Obviously, we could solve this by dividing by 6, factoring it, and all kinds of good stuff like that, but we'd just be getting started instead of, hey, we're done. Now, what we're going to do is we have our two values of x where we have possible critical values. I'm going to set up a number line. Then what I'm going to do is I'm going to evaluate my function on each of the intervals represented on this number line. First, I'm going to evaluate the function to the left of -1. Now, there are an infinite number of choices that you have. I'm going to keep it simple. I'm going to go with -2. Then, between -1 and positive 2.5, we get to pick any number we want. Infinite number of choices. I'll keep it simple, and I'm going to use 0. To the right of 2.5, well, let's see, I'll keep it simple again, and I'll pick 3. At this point, what I need to be able to do is to evaluate the derivative at 3 locations. I can do this all by hand. I could substitute the -2, the 0, and the +3 into my derivative. But, the thought is, hey, I'm going to be doing the same thing a whole lot here, potential for a lot of mistakes. So what I've done instead is I've done two things. Notice in y1, I've put the original equation, and in y2, I have put the derivative. I always, always, always put the original function in y1, the derivative in y2, not because the calculator will give wrong answers if you don't, but it keeps things straight in my head. I know that y1 is always going to be the function, which is the y value, and y2 is always going to be the derivative, which is the slope. Then I go to the table, and I'm going to get rid of that. Now the cool thing is, I can look over here and see I want to evaluate at -2. So I pop in -2, and look what it does. It gives me two things at once. Remember, y1 was my y value. Aha! So I can jot this down over here, and I have a location here. Well, don't want that to disappear like that right now. Okay. At -2, the y value is 17, but notice what the slope is. The slope is 54. Okay, which tells me that the slope is greater than 0. And if the slope is greater than 0, this thing is increasing. All right, then I go to my second value that I want to consider. This is where the derivative is 0. So I'm going to put in 0, press enter, and let's see what happens here. Remember, for right now, I'm not concerned about the y value. I'm only concerned about the slope. Here, the slope is a -30. So I can come over to here and put down, gosh, this is less than 0. That means it is a negative slope. It's going down. It is decreasing. Then I can evaluate the function, actually the derivative, at 3. Press enter. Now the derivative, the y2, is going to be a positive 24, which means that it's greater than 0. The slope is greater than 0. The derivative is greater than 0, which means the function's increasing. Okay, so let's take this information that we have. To the far left, we're increasing. Just past that, we are decreasing. Aha! What we have here is a critical value. This critical value is going to be a maximum. The critical point, be careful, there's a difference between a critical value and a critical point. The critical point is going to be where the x value is -1, and I need to get the y value to have a point. We'll get back to that. Let's move into the second and third intervals. The middle interval is decreasing. The rightmost interval is increasing. This indicates that we have a change here. This is going to be a critical value again. And this time, we can tell that the critical value is going to be a minimum. It's not always going to alternate max min, max min. The critical point occurs at an x value of 2.5, and I need to get the y value. Okay, so I have critical values at x equals -1 and x equals 2.5. Be really careful. Critical value and critical point sound dangerously similar to one another, but they mean very different things. The critical value is just give me what the x value is. The critical point is an x value as well as a y value. Okay, so let's get these critical points. To get the critical points, I need to know what the y value is when, for example, x is -1. So I'm going to pop in -1 here. I'm going to press enter. And notice this time I'm not looking for the slope, but notice what the slope is. The slope is 0. This should not be a surprise because remember, we solved our slope equation. This equation right here equal to 0. So it should be that the slope works out to be 0, which is exactly what we're getting for our slope. But what we're interested in right now is the y value. Notice the y value is 42. So for my critical point, my x value is -1. My y value is 42. Then to get this second critical point, my x value is 2.5. I need to plug in a y value. So I'm going to put in 2.5, press enter, and be really careful here. Notice the derivative, the y2 is once again 0 for the exact same reason as the previous one was 0. And our y value is a -43.75. Okay, so I can put in this -43.75 there. It makes sense that this left point is a maximum. Look at the y value. It's positive and way up there. It makes sense that the second critical point is a minimum. Look at the y value. It's negative and it's significantly below the x-axis. What you need to be able to do at this point is to be able to walk up to a function, locate the critical values, determine if they're maxes or minimums, and then also determine the critical points. With that in mind, let's take a look at another example, and I'm going to ask you to solve this on your own. So on this one, you're going to need to pause the video, figure out what's going on, and go from there. Okay, so let's take a look at a second example. At this point, the examples are fairly straightforward. We're only going to have one or two critical values. Okay, let's say that we have something like f of x is equal to 2x cubed minus x to the fourth. Okay, what I would encourage you to do is to first compute the derivative. From that derivative, go ahead and determine what the critical values are. Determine on what intervals the function is increasing and decreasing. Identify if the critical values are a maximum or a minimum. And then determine the critical points. So go ahead, pause your video, and work through as much of that as you can. Well, hopefully you actually did pause the video and give this a shot. Remember, as you're working through a problem, if you get stuck, you can always move the video back and look at a previous example to help you figure it out as well. Anyway, so let's take a look at this. The derivative is going to be 6x squared minus 4x to the third. Because we are looking for critical values, places where the slope is 0, that means we're going to take this derivative and set it equal to 0. To solve this, perhaps the first good maneuver would be to factor out a 2 and an x squared. Factoring out a 2x squared from this first term will leave us with a 3. Factoring out a 2x squared from this second term is going to leave us with a minus 2x equals 0. Now, one of the things that a lot of people don't understand is when you get to this point, you can take and set both factors equal to 0. So what this essentially says is we can do this 2x squared equals 0, and we do this 3 minus 2x equals 0. That part most people get. But what a lot of people don't understand is, oh, why can you do that? Why can you take each of the factors and set it equal to 0? The answer is actually pretty straightforward. If you have two factors being multiplied together and the product is 0, one or both of those factors has to be 0, because the only way you can get a product with a 0 is if one of the numbers being multiplied in your product is 0 itself. So that's what allows us to say, well, maybe it's the 2x squared that's 0, or maybe it's the 3 minus 2x that's 0. Solving this first one, we get x equals 0 as a possible critical value. Solving this second one, we get 3 equals 2x, or we get x is equal to 3 halves. Okay, with that, I'm now going to create a number line, and this number line is going to have the values 0 and 3 halves. Remember, 3 halves is 1.5. Just as we did in the previous one, I want to evaluate the derivative in each of the intervals on this number line. To do that, I'm going to do just like I did earlier. I'm going to set up my calculator where y1 is equal to the function 2x cubed minus x to the fourth, and y2 is going to be equal to the derivative 6x squared minus 4x cubed. Setting up my calculator is just as simple as going to y equals, and in y1 I just put the 2x cubed minus x to the fourth, and in the second one, y2, do the 6x squared minus 4x cubed. Then what I'm going to do is, just like earlier, I'll go to the table, and this time I'm going to get rid of these values, and I'm going to use my new values that I'm interested in. Remember, the first thing I want to do is evaluate the function's derivative. So that means I need something first to the left of zeros, like -1. In this middle interval, I can't use 0 this time because 0 is the end point, but I can use +1. And then to the right of 3 halves, I can use something like 2. So what I'm going to do is use these three values of x to determine if the derivative is positive or negative. So I pull up my calculator. To the far left, I'm going to enter the -1. And remember, at this point, I'm only interested in derivatives. In this case, the derivative is 10, which is greater than 0. When I then move to my middle interval, I'm going to use a value of x equals 1. Then I'm going to look at my derivative, which is my y2 value. Well, that's kind of weird. This is positive as well. That's entirely possible. They do not always alternate positive, negative, positive, negative. It's entirely possible for all three of these derivatives to be positive, for all three of them to be negative or for them to alternate. Okay, on to the third one. I'm going to evaluate the derivative at 2. Now notice here, the derivative at 2 is a negative 8. I'm not real concerned about being negative 8, just know that it's negative. Okay, so now that I have, move this up a little bit, these values, on this leftmost interval, the slope is positive. That means the function is increasing. On the middle interval, the slope is positive. That means the function is increasing. On the rightmost interval, the slope is negative, which means the function is decreasing. That tells me that my function is going up. It hits a slope of 0, continues up, hits a slope of 0, and then comes down. Well, I kind of missed that a little bit. Going up, hits a slope of 0, going up, hits a slope of 0, and then comes down. I have a graph like this. Now, it's important to be able to interpret what's going on here because this is not a critical value. It's not a maximum. It's not a minimum. It's not a location where it's undefined. It's just a place where it levels off and keeps going. This is a critical value. X equals 3/2 is a critical value. In this case, what we have is a maximum. It goes from increasing to decreasing, so it's a maximum. We can compute the critical point, which is going to be the point where the x value is 1.5. And now I need to compute the y value. Well, that's not too bad to do. I'm just going to get out the calculator, and I'm going to put in my next x value, which is 1.5. Now be really careful here. Notice the slope is 0. That's fine. That was what was expected, okay, because this is a location where we solve for the slope to be 0. The y values is 1.6875. I'm going to put well, let's just go ahead and put that down. So it's going to be 1.6875, and there is a critical point. Something to notice here, at 0, while it's not a critical value, it is kind of an interesting point. So I'm going to go ahead, plug 0 in, and I'm going to look at what is the y value when the x value is 0. So this gives me the x value is 0 and the y value is 0. With this information, okay, and you can see I've already sort of got a graph sketch there in green, but what we can do is we can put in a graph. Now, notice here, I was careful where I put my graph. I put my graph so that the x equals 0 lines up with the y-axis. At x equals 0, we have a point 0, 0. Then when I come over to x equals 1.5, so here's 1, here's 2, at this 1.5, which is right about here, I have a y value. I'm just kind of guessing where that is. This is going to be 1.5, comma, 1.6875. So a y value of 2 would be about here. A y value of 1 would be about there. With this information that I have, first, I know to the left of 0, 0, the function is going up. It levels off at 0, 0. Then it continues up. It levels off at this 1.5, and then it goes down. You can actually now sketch a graph of the function based on this information that you have here between the value of the critical point and Where's the function increasing and decreasing? So realize that this information that you have here between the function and the first derivative is very powerful. It allows you to identify where's the function increasing, where's the function decreasing. Okay. It allows you to draw a sketch of the function. There's a lot that can be done with this. At this point, I'm going to call quits on this video. I am going to see about putting in another video for this section that just does a couple more problems for you to work on. But for right now, that's enough.